talk about probably lots of small and simple thinking that we aggregate together into a really good overall picture of a mining operation and valuation of a mine and a mining technology. So, as Susanna said, I'm at Redwood. I've been working at Whittle Consulting for about 5 years. And I think a lot of you would have been exposed to Whittle, the name, Whittle Consulting. Gerald Whittle would have given talks to many of you. Can we have a show of hands of how many have seen Gerald talk? Okay, lots of you. Well, that's quite good because I'm planning to do a very short overview of generally what Whittle Consulting does, the integrated strategic planning. And then I'm going to switch over to talk about two particular case studies we did. So this is a different approach, a different usage of the technology that we have and the methodology, which helps us to value mining technologies or mining processes. And these things are typically very difficult to value. It's very easy to put together a small, narrow valuation of something like ore sorting, but that does not capture the vast majority of the value of a technology like that, and that's what we're going to talk about today. So our overview of Whittle Consulting and strategic planning. We've worked over the last 15 years for a large number of companies around the world. I'd say this is only a small fraction of who we've worked with. And throughout those 15 years, Gerald Whittle has been pushing the philosophy of it's a money mine, the purpose of a mining operation is to extract money from the ground, and the way to do that is to increase the flow of the money through the system. And that approach can be extended to take into account sustainability and environmental social impacts, which has been one of the developments in more recent years. So the company started, the initial company started 30 years ago with development of optimization software just to optimize a pit, an open pit, Lewis Grossman algorithm, and it's progressed over time to what we use today, which is this particular piece of software, which is all around optimizing everything from the resource that's in the ground through to the everything between the resource in the ground and the market, which are the two things we can't control. And doing that with respect to the constraints in the system, the bottlenecks. So that's some words around that. Some of the key things that we use and are essential for building these sorts of models are these things here. I'll mention a couple quickly. The theory of constraints is very fundamental to what we do. So in order to push our money flows through the system, we need to understand where the constraints are, what stops us from accelerating flows, and that ties in with considering the time value of money. So I know there's various opinions around about how important time value of money is, but we certainly believe that it's of very high importance that cash flow today is better than cash flow tomorrow or next year, because it provides risk mitigation. It's essentially a good thing. I'll also mention activity-based costing, which is it's really just about ensuring that we have an accurate picture of what the drivers are within a mine. So an example I often use is that someone will ask for a mining cost and someone else will say, well, it's $1.60 a tonne. End of conversation. Well, you need to at least dig down a little deeper than that in order to have a good picture of what's going on. You need to find what the drivers are, so an obvious one would be the length of the distance that the truck has to drive from the point of collecting the material to the exit of the pit. So you should take into account that consideration, and you should at the very least split out fixed costs, variable costs, startup costs, shutdown costs. So overall this is all about getting an accurate picture by getting a small thing right here, there, and everywhere, rather than really getting a detailed picture from one particular component. Obviously that would be nice too, but we prefer the former. And that leads into a philosophy of what is the value what is the goal, what is the value that we're trying to create. And typically, Whittle Consulting has always used net present value as the most important goal. And as I mentioned before, there's been some move in recent years to have some sorts of combined goals that include social and environmental capital. So here is another schematic of what a mine looks like. We can't control resource, we can't control the market, because we're price takers. The market price is set by someone else. We can control everything in between, which are all different parts of the operation. So we have, I don't know if many of you can read that, it's quite small, but we have the pit and phase shape, or the underground shape. We have what we mine and when, the schedule. We have policies we pursue to decide our cut-offs and our blends. We have stockpiling strategy, and then we have lots and lots of levers to pull in the plant to decide what gets through and what the costs are and all of that. And finally, we have product mix and logistics. And the really important thing to note here is that these things affect these things, and these things affect these things. Everything downstream everything downstream obviously receives its material from what's upstream. So in that sense, they're completely dependent on what's upstream. But also everything upstream, and this is especially important for the mining and geology people, everything upstream, their economic context and their social and environmental context is all determined by what occurs downstream. So the plant is essentially, and the market is essentially valuing what's in the ground. And so people need to be aware of, if you're in the plant, you need to be aware of what's going on in the mine and vice versa. So we've done lots of optimization projects for mining companies in the last 15 years. The usual process is very simple. It's like this. We start with a schedule, a plan, pit shapes, plant settings, all defined by the client. That's the base case. And then we re-optimize everything piece by piece, step by step, somewhat similar to the arrow diagrams before. And we get an optimized case. All good. But there's a second usage of this technology, which we've been investigating in more recent years, and it hasn't been a commercial usage, so we haven't really made money from this or anything. But it's a very useful approach, and that's that we can value mining technologies and processes, practices, things like that, using the same software. So we take a known optimized schedule, which might be this one here, and we call that our base case. So it has already had the optimizer run over it. It's a good schedule in that sense, and it doesn't have a certain technology. And then we drop in a technology, and we look at the differential. So that's good because, as I said before, you can try and value some technologies like ore sorting technologies, which fundamentally affect lots of different parts of the system. You can try and look at that in isolation, but it's really difficult. The valuation of that is much more dependent on the context of a particular mine, particular processing system. Everything else is needed. You need to know everything else in order to value technology. And so this helps us answer this really difficult question of what is the value of this mining technology or process. So in the last few years, we've done a few case studies. I did these four. CRC or grade engineering, which is one I'll talk about today. Obviously, a lot of you in Queensland will be very familiar with this, or will know the people involved. SHOVELSENSE is a similar one, which we'll talk about as well. And I've also looked at autonomous mining systems, a small mining technology that helps you decrease pit slope, which is edge protector, and one of my colleagues looked at ultra-high intensity blast schedules. So in all cases, we try to value the technology within a fictional but realistic mine. So as I said, it's basically 3 presentations today, so now we get on to the second one, and this is talking about the CRC or grade engineering. Kind of getting a show of hands of who knows about grade engineering. Yeah, most people again. I will explain it quickly, but many of you probably know more about the details of it anyway. So as I said, we need to start with a base case. And so this schematic shows what's almost the canonical base case for these sorts of case studies. So it has the basic components that we need for a mining operation without, and to demonstrate all the features without skipping over anything. So we have a fictional mining body called Marvin. We have dozens of versions of this thing. I think it's been used for about 30 years by various people to demonstrate various technologies and that. We have processes, which are these squares. All of these have cost associated. They have consumption of units, which might be bottleneck units or might be constrained units, like truck hours or energy requirements in the plant, in the mill. We have stockpiles, and we have at least two processing paths. So we have a heap leach for low value material or oxides, and a ball mill for, a flotation plant for higher value material, higher recoveries, typically better recoveries for the fresh material. And within the ball mill, we always try and have at least, within the plant, we always try and have at least one variable feature, and then nearly always the most important one is the hardness of the material, and that's its interaction with different grind size approaches, and those all have costs associated, they have throughputs associated, and they have different recoveries associated. So I'll spend a bit of time talking about that because that's just the basis of this case study, and in fact the next case study as well. A very simple and similar operation. Yeah, so this just says there's lots of settings. We don't need to worry about what those are. So we run our optimization. It produces a schedule. It mines out the Marvin ore body, or it mines as much as it wants to of the Marvin ore body over 11, 12 years here. We get a cash flow graph. We get a big capital cost up front, just like most mining operations, and then we get various cash flows over the course of the years. And because we care about the net present value, not about just individual cash flows, we get a cumulative discounted cash to reach our final NPV, which is about 628 million. So that's our base case. Does anyone have any questions about anything I said there? No? Alright. Yes, well, that's to show it's fictional. Right, and it's to avoid people saying, oh, the copper price today is not exactly that.
Negative cost after the completion.
What's that?
Negative cash flow after completion.
Oh, there probably should be one of those for the shutdown. Yes, you're right. The problem with that in optimizers is that the optimizer will always try and avoid that cost. So you normally add it afterwards. Now, I don't want to go, there's obviously masses of information that can come out of that particular set of runs. I don't want to talk about all of those things. I'll just talk about one chart, or this chart, which shows the main cost driver in the system is through the processing plant, and we have a constraint which is 200 million kilowatt hours is the maximum amount of energy in a year that the ball mill can apply to material, and that's the bottleneck in the system. Because we allow different grind approaches, we have both a fine grind in the red being used by the optimizer, and a coarse grind in the purple being used by the optimizer. So it's decided that for some material it's much better to fine grind it, get out more of the copper and gold. In fact, there's copper and gold in this, and accept a lower throughput or greater bottleneck consumption. And for other material, it's better to push it through the system faster and accept a lower recovery. And that's typically the lower grade material, and the high grade material gets fine grinded. So that means that this is the same plant system basically. It means we get a variable mass throughput through the plant each year. Hopefully we're not limited by other constraints like pumps and pipes and material handling equipment. If we were, we probably should buy more of those because it's much better to have a bottleneck in the place that's really expensive, which is the plant. And the other key characteristic of this is just that we get high grades going through the plant early, and that decreases down to some sort of marginal cut-off grade towards the end. So those are things that we wanted to see in a lot of, wherever possible, in mining operations in a good schedule. And indeed, this is the base case, and it's already been optimised, so it does have those characteristics. Then we need to drop in the grade engineering technology. So grade engineering technology suite, at this stage anyway, when we did the study a couple of years ago, was screening, which you all know about, which is great when you've got material that, say, has a coarse component and a fine component, and the minerals that you want are disproportionately in either the fines or the coarse component. In this case, we've said that most of the copper and gold is in the fines component. If you can't just screen material to separate these things out, then for some ore bodies or for some types of rock, you can blow it up to a finer degree than you might otherwise, and cause it to separate out into a high-grade fine fraction and a low-grade coarse fraction, or vice versa. So that's termed induced deportment rather than natural deportment, and then you screen it again and get out the proportion that's the one you want. And the bulk sorting technology is where you have some sort of sensor going over a conveyor belt, and that helps you, they can identify in real time some approximation of the grade of the material going through it, and then flip a switch to go either one way or another into the plant or else off to somewhere else to be handled. So that's the technology suite. And so because we're doing we want to look at all of these together, so we just did every combination of dropping these into our existing model, all the way from the base case where we don't have any of them to the final case where we've got all of them turned on. So we had to have, within the ore body, for grade engineering to be important, you have to have a response so the rock has to respond to that technique well or not well. And so there's varying degrees to which it may respond, and so in this case we tried to model, we had 6 different rock types, and we said that some respond really significantly to certain grade engineering technologies, and some have no response at all. So this chart, apologies for anyone who's colourblind, but apparently humans are very good at picking up different shades of green, so that's why I've got green. If you assumed you had a block of material or a portion of material of this grade, and you put it through one of these processes, like say bulk sort 2 here, if it's a fresh type 1 material, then it will give you out a small portion with a much higher grade and a large portion with a much lower grade. So we can see that for all of these fresh type materials here, we have a high response to bulk sort. For oxides and transitional 1, we have some response to screening. Differential blast was only applicable to transitional material in this particular case study, so it has a reasonably high response, and this TR2 type has no particular response to anything, so it's probably not very much point in applying these techniques to that particular material type. And so the grade engineering guys, Mike Scott was the main one we talked with, we're really keen to have a wide array of different rock types that respond in different ways to this technology. So here's our processing system now. Obviously it's really complicated. This is the one with everything enabled, all the features. But you can essentially see it as having mining like we had last time, having the ball mill and the heap leach over here, and all the grade engineering stuff is optional in between. And you can have any combination of those things. You can only choose one, rather. You can't choose to bulk sort and then screen material, we didn't allow that, but you can choose one of those things, or you can bypass, as we saw is probably necessary for that transitional 2 material. for each of these, say where it's got 5 different options here, those just mean it can go through one screen type and not the other. And so we get an output from running all these optimizations, and the best case with all the features turned on has slightly higher earlier cash flows, and overall the net present value has increased. Now I know that we did this relatively conservatively with a lot of the parameters at the request of CRC OR, so it's only slightly higher than the previous one, but nevertheless it's about a 10% increase, which I've located to there. So that was our result. The other important thing to note here is that this particular option with differential blast allowed, bulk sort allowed, but no screening, it got basically the same value as the one with all the options turned on, and that's because those different features essentially compete for the same material. Now I'll flick back to, I will show this chart quickly. There are lots of charts in this presentation, overlay charts. This shows the differential between, if we look at the brown lines and the gold lines, this shows the differential between our everything on grade engineering approach and our base case approach. And we can immediately see that how we're getting the higher value is by having a higher grade early on. So copper grade, which is the solid line, is higher than it was in the base case, which is the dotted brown line, similar for gold. So we can see higher grades early on, obviously a good thing for net present value. But that doesn't necessarily say how exactly we've created this value. So that's the question here. How is the value made by these technologies? And this is where, probably not people in this room, but I've seen even recently an ore sorting technology being publicised, and it was all written up about saving cost. So you take away gain from the plant, i.e. the low value stuff, you don't put it through the plant, and therefore you save cost. Well, that really misses the point, and especially when the plant is the bottleneck, the ball is the bottleneck, which it is, you're not going to leave some of your bottleneck plant vacant. You're not going to not use that capacity. You have to replace that material that's vacated because it was low grade, low value. You have to replace it with something good. And so there are 3 mechanisms, all of which we observed in this case study, just from the optimiser's behaviour, not from just telling it to do anything. 3 mechanisms that we observed to fill that space in the plant. So if you imagine, I may not explain some of that well, if you imagine previously in the base case we had all this material going through the plant, we've instead used some great engineering technologies to get a high value portion and a low value portion. The low value portion goes somewhere else. Now we have space in the plant that we can use for something. We obviously want to put more high grade, high value stuff through it. Where can we get that material from? Well, first option is called metal exchange. That's a term coined by CRC OR, and that's what they use. That's when you have another stream of material that was going to a low value location. You use the great engineering on that, extract a high value portion, and you put that into the plant. So you basically swapped between the low value stream and the high value stream. You're taking the worst from this, put it down there. You're taking the best from the low value stream, put it up there. They swap positions, and everyone's better off. You're putting a lot more value through your plant. Another important way is to increase the mining rate so that you get deeper, get more high value material out faster, provided you don't run into mining limits, such as the vertical rate of advance limit, which we did in this case. So with these technologies in place, we saw an approach where you actually mine the ore body out faster, you filter out the best stuff more quickly, put that through the mill, use more stockpiling if you can, and process that later. And that's all owing to having created space in the plant, which takes pressure off the plant. The final way that we saw an increase in value, or to use up that vacated plant capacity, is by using more of the high value streams, the high value options, processing options. So that was fine grind, right? So if some of that material is vacated the plant, and some of the remaining material was previously planned to be coarse ground, because you've taken pressure off the plant, you can now fine grind that and extract more product from it, rather than having to coarse grind it in order to fit more through. So it might sound kind of informal saying take pressure off the plant, but there is actually a solid mathematical basis for that. And when you do take pressure off something, you do allow the other things to kind of expand into that space. The other processing streams to expand into that space where they're high value. And this is the other benefit touted of grain engineering, or of ore sorting type technologies by some people, which is really actually extremely minor. It's basically just that the very low grade material that you're extracting from the mine, previously some of that would be just below the cut-off grade, the marginal cut-off grade, you wouldn't process it. But instead, because of grade engineering, you can extract a slightly higher value portion, and your ultimate cut-off grade leaving the mine, actually at the end of the life, goes slightly lower. We did observe that, but it's extremely minor because it's by its nature low grade material that you're processing right at the end of the mine's life. This final chart on this particular topic is just showing that thing I mentioned earlier, which is that if you apply these technologies one after another, you add them to an existing system, you don't get a cumulative benefit. So you can't say screening improves NPV by 3% and differential blast by 4% and bulk sort by 5%, and they're all added together. No, because valuation, as we've discussed, is always within a context, and once you have other material that once you have material, as in this case, that could be sent through a screen from the outset, or it could be differentially blasted to achieve a similar result, you're not going to need both of them. So we actually found that if you have the ultimate benefit with everything turned on, you get basically the same benefit with just bulk sort and differential blast in this particular mining operation. That's not a general conclusion. That's only saying for this particular mining operation, with these particular rock types that respond in these particular ways to the technology. So it's really just showing it's not additive. So a quick conclusion from talking about this case study. You need to use a holistic or systematic approach to valuing technologies. It needs to incorporate everything between the resource body and the market, and it needs to consider an accurate view of the system, and it needs to consider, very importantly, the bottlenecks in the system. For something like ore sorting technologies which affect those bottlenecks, you really can't value them any other way, I don't think. So that's a CRC ore case study. Now move on, how am I going time? All right. We'll now move on to the SHOVELSENSE case study. So MineSense is a Canadian mining technology company. They build sensing equipment for mining operations, where you apply the sensor to rock going over a conveyor or passing through it in some other way, and it provides a real-time reading on initially copper grades, and I think they've got copper, gold, lead, zinc, some other things in production and testing as well. But this particular one, we're talking about SHOVELSENSE. So they put these sensors all over plants and everywhere, but here they fit into a excavation shovel. This picture doesn't really show a lot because there's not really a lot to see, but basically you attach the sensor to the shovel, and it will provide a real-time reading, and it's accurate within, I think, like 10% or something like that of the copper grade of the material within the shovel. So how do we set up a case study for this technology? It's a bit different to the previous ones because it's working in a different location, essentially in the mine. It's working where the shovel picks up material. And the benefit there is that instead of doing our grade control on a whole block, which might be 10 by 10 by 10 or 20 by 20 by 20 meters or some other large volume, instead of deciding the whole block has to go a certain processing path to the plant, to the dump, to the stockpile, we can instead decide on a much smaller volume, a shovel load ideally. So that's what this shows. So the worst case grade control is when you make your decision for a whole block and you send it all one way based on sampling points. We talked about industry best practice, or better practice anyway, which we were told was that you have 4 drill holes per one of these columns, I suppose we can call it, or a grade control unit, which I think 1 metre or 2 metre spacings, and that essentially you do 4 samples within this column, and you define the column grade based on those 4 sampling points, and that's certainly more accurate than this, and then you can send just that column on a certain processing path. So certainly a lot better, or it looks a lot better on the face of it anyway. Then we go over here, which is this ideal case enabled by the MineSense technology, the SHOVELSENSE technology, where we can do our grade control based on the volume of a single shovel load, which in this case I've chosen quite a large shovel, 23 cubic meters. Now that is best case because in order to be able to send the material to its destination based on a shovel load, you need to be able to load at least 2 trucks side by side from your excavator so that you can separate out a higher value stream and a lower value stream. If you can't, then you are limited to essentially doing the grade control back on a truck volume rather than a shovel volume. And we chose a realistic case which they thought was the most likely, which is that 50% of the time you can do double-sided loading, which enables this, and the other 50% of the time you can't fit 2 trucks, so you'll do single-sided loading, in which case your grade control is at a truck volume level. The other benefit of the technology that's not shown here, or that's not taken into account, but is certainly important, is that these techniques for estimating grade are all done before the material is blasted. So you're taking these assays or the samples from here, calculating the grade, saying that's the grade of the column, then blowing it up, and then finding that obviously what you get ultimately is a little bit different from what you estimated. Whereas the shovel, you've already blasted it, and so you're just measuring exactly what's there and what's going to the plant. This is a chart that really captures the effect of this. So again, if we start with a single block, which is this grey line, it's got 0.6% copper, this particular one, and we are treating it as one big chunk, which is 0.6% copper all the way through, and we're just going to treat it like that. Whereas the best case, if we take out lots of shovel loads from the block, these distributions were given by MineSense based on their experience and pilot runs in the field. You get lots of little chunks of material, and some of them are really much higher grade, and some of them are much lower grade. So we can immediately see the benefit of this, which is that the higher grade is going to go straight to the plant, the highest value processing route. The lowest grade, we can get rid of it and send it to the dump. And so we've immediately got back to that situation like we talked about previously with the CRC ore, where we've got a large potential for metal exchange between different processing streams. Clearly in between is the column and the truck options, which are sort of these middling ones. And it was interesting to me to see, based on the test data, that it didn't make a lot of difference really when you've got just going from a single block, treating it as a whole block to treating it as a column. In fact, there's even a huge difference between treating it as a truckload at 120 cubic metres versus treating it as a shovel load at 20 cubic metres. You really get down into the differentiation of the ore body if you can go that extra finer step. And remembering that the whole point of all of our processing plant and everything is to extract the highest grade stuff from the lowest grade stuff. This is already doing a lot of work for us. So we set up our base case. Again, in order to value this technology, we need a base case. And this is extremely similar to the one I showed before. In fact, it's basically identical. The only difference this time is that we have the Marvin ore body segregated out by the type of mining method that we're using. I don't need to go into details of how that happens. We get a base case result. In this case, it's 274 million MPV. We get a big capital loading up front. We get some high grade starting off, or some high value stuff starting off. It decreases for a while, then we hit another pocket of high grade, and it decreases a while until we process the stockpiles at the end. This chart just shows sort of the material movements. It's probably a bit more detail than we need to go into. But this is the base case. We have all of the mining, all the material movements is the size of the bar. Some of that is to stockpile, some of it's rehandled from stockpile over here. We have a variable mining rate, which this is very variable. We could possibly decrease the variability of it a little, but we are very much against declaring a flat mining rate, because that means you're missing out on some potential there. And the important thing is that our grades of copper and gold going through the processing plant are here, and they start off highish and then go lower. So that's our material movements, shows some of our drivers of value. So what happened when we drop in the mindset and its technology? Well, that base case, by the way, was for the column, not for the worst case, which is the block. Because we wanted to kind of give some credit to the mining industry that they do things slightly better than a whole block grade control. So what happens when you take a step back from doing that good practice grade control to a whole block? Not actually a huge amount of loss of MPV. It was only minus 9 million. So relatively small, and considering we're talking about a 12-year operation here, that's kind of within the margin of error, you could kind of think. If we increase our resolution though, we're soon seeing it starts to make a really big difference. Until we get up to this per shovel best case, or in fact perhaps I should talk about this one, more realistic case, the 50% shovel, 50% truck. We really are adding a lot of MPV just by doing this pre-separation that the SHOVELSENSE technology, or in fact other ore sorting technologies, can enable for us. So I did look at this both when you optimize, when you re-optimize only everything downstream of the pit shape itself, and then once you redesign the pit, there's where you get a little bit more, because you should redesign the pit whenever you change something major like this, because the economics of the pit have changed. So all up, we get an increase of 128 million to our NPV, and that's pretty major. Here's a differential chart showing the same thing. And yeah, our NPV, our cash flows are higher from the outset than they were previously, and they finalise at a much higher NPV. So we're happy with that. This again shows the increase in grades going through the plant versus what was in the base case. It was, copper grade was in brown. And there's grade to leach as well, which is much less important, much lower value. In fact, it's not even higher. This one is higher. The copper grade going through the plant, because of the MineSense technology, is now much higher than it was before. So good. And again, The mechanisms by which this value is achieved are exactly the same as they were for the CRC ore technology. So it's metal exchange, or it's vacating room in the plant. It's exchanging that lower value material we took out with higher value portions from other material. It's increasing the mining rate, if we can, in order to find more high value material and filter it through the ore body faster. And it's using high value processing streams. I don't think we observed that in this one, but in theory, again, you can switch more of your material to a fine grind because you've made space in the plant. So that ends my talk. There are the full write-ups for all of these, both of these case studies on our website. I think I included links in the opening pages. The summary, again, was that we need a holistic, overall integrated way of valuing technologies or doing mining enterprise optimizations. But in this case, we need to be able to look at the whole system in order to work out how important our ore sorting technologies are, especially because they are really resistant to valuing using other methods, and yet they are tremendously important. Thank you.
So thank you very much, Nick. Very interesting.